All right, welcome back. Sorry about that. We hit an hour, and that is the maximum recording time for this software. But what we were talking about is overtones, two tones produced by an instrument that have the same harmonics. The harmonics with the highest amplitudes will constructively interfere. An example of this is a violin and a viola. So a violin plays an A that is an octave lower than the viola plays an A that's an octave lower than the violin, and we can see the frequency analysis here. So here would be 440, and here would be 880, and then here would be the next, which is what, 1320, and then here we would have 440, 880, 1320. And then here we have a peak, so that's 220 times 11. And that is 20, there we go, 2420. And then we would have, so this would be somewhere close to that, or actually this would be, these would be the most closest. So we would have this one and that one. Anyways, the point being that the base frequency in this case is 220 is the fundamental, and this one is 440. However, they have these matching higher harmonics that will sum together. So when you put this 1320 on top of this 1320, the result is going to be somewhere up here, which is almost as loud in amplitude as the original 440. So you would hear this 1320, so this note that is 1320 hertz. You would hear that amplified, even though the base frequencies are 220 and 440. Last thing we have to talk about is the Doppler effect. So the Doppler effect is a change in frequency or wavelength of a wave for an observer moving relative to its source. Relative to its source. So we've all experienced this with a car or a fire truck or any loud noise that is moving towards you, then drives past you, and then moves away from you. So this sort of sound, it gets higher in frequency, and then when it passes you, it decreases. So this lower frequency after it starts moving away from you. So if the source of the sound, it's usually sound, it actually can be any wave. If the source of the sound or wave is moving towards you, the perceived frequency by you, the observer, will be higher. And if the source is moving away from you, the perceived frequency will be lower. The key here is that the source frequency is unchanged. So a fire truck has its siren on. The frequency of sound that the siren is producing does not change. It stays the same. It's only the observer who experiences a change in the frequency that they hear. So let's look at this as a representation of a sound source. We can see that an observer right here would be receiving sound waves at the same frequency, right? They're hitting him or her or it at the same frequency that they are being emitted by the source. And that can happen anywhere you want. Same thing will happen. You'll get the frequency is the same no matter where you are. However, let's picture a moving source. If I am a source right here, right, I will be getting waves that are a lot closer. They are a lot closer because essentially the sound source is catching up with the waves that it already sent out. So this first wave, it is moving towards it after it releases. It releases that first wave and then it kind of chases it. as it is releasing more waves. So those waves get closer and closer and closer together, and if velocity is frequency times wavelength, if wavelength goes down, frequency must go up because the speed of sound is constant. So the frequency that you hear as the source is moving towards you gets higher. Conversely, if you are over here, those waves, the waves that the source is sending out, are moving further and further away from each other as the source is moving. So you hear a lower frequency than you normally would. And interestingly, as you break, what they call breaking the sound barrier, is when you are moving at the same speed that sound does. So you are immediately catching up with those sound waves that you are creating in front of you. If you were sitting on the wing of an airplane, moving at the speed of sound, you would not be able to hear somebody next to you. You could shoot a sound, you could hold an air horn in front of your face and blow it, and you would not be able to hear anything because the sound moving at 340 meters per second is the same speed that you are moving. So this is why you get shock waves. Shock waves are a buildup of the pressure of the sound waves that you are catching up to. You're shoving more air at this sound wave that can't get out of the way fast enough because you are moving too fast. If you would like a formula for the Doppler effect, so the frequency change due to the Doppler effect, this will not be on the AP exam if you are an AP student, I believe. It's not on your formula sheet, so they shouldn't expect you to know this. However, you should know how it works. So the perceived frequency, so this is the perceived frequency, and this is the emitted frequency. The perceived frequency is multiplied by this coefficient where you have c is the speed of the waves, VR is the velocity of the receiver relative to this medium, and Vs is the speed of the source relative to the medium. So VR is positive if the receiver is moving towards the source, and Vs is positive if the source is moving away from the receiver, right? So that is just a little piece of information. So that's the Doppler effect. You mostly need to understand it conceptually. All right, and that just about does it. Thanks for watching. If you have any questions, you could leave a question in the comments, and I can get back to you as soon as possible, or just see me in class or after school. Thank you very much.